Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we tackle 6.6, which is putting all the knowledge we learned together into one section. Before we jump into 6.6, we've got a little bit of a thinking question on our hands. If you look on page 11 of the packet, we have the question, match each equation with the graph of its related system of equations. Then we have to basically use the graph to solve the solution. What on earth does that mean? Well, what we have here are 6 different equations, 6 different graphs, and we're trying to match them so that we know which is which. After that, remember that wherever 2 lines cross is the solution of their system. So we want to find what the solution is. Okay, well, as we're looking through here, the first thing we notice is we've got a ton of different shapes. 5 of them have a straight line as well as a curved line, and one of them, A, has 2 curved lines. What makes that shape? What would make a shape that goes up and to the right or down and to the left? Well, we know from all the way back in 6.1 that those are exponential functions. Exponential functions either go up to the right or down to the left. Since there are 2 of them, we can surmise that there are 2 exponential equations we're trying to compare. And in fact, there's only one equation that has 2 exponential functions. C, 2 to the x power equals 3 to the negative x power. When we are trying to find these solutions, either side of the equal sign we can treat as its own line. Where they cross will be the solution. So C is going to be of graph A. And the solution, where that dot is, where they cross, it looks like it's just going to be 0, 1. Before we do that, let's check to make sure with our equation that this works. So we think that the solution to 2x equals 3 to the negative x is plugging in 0 for x and getting 1 for y. There's no y here really, so we don't need to really plug in the y value. We just need to plug in the x value and see if we end up with a true statement. So is 2 to the 0 equal to 3 to the negative 0? I think it absolutely is, because 2 to the 0 is 1, and 3 to the negative 0 we treat as 1. 1 equals 1. Let's take a look at our graphs once again. We realize that we have 3 graphs that sort of curve like so, and 2 graphs that are exponential. Similarly, we have 2 graphs that are exponential, and 3 graphs that are not exponential. Let's take a look. One of our exponential graphs is e to the x power equals 2. And the other one is 4 to the x power equals 2. The fun thing about these is we notice that both of them equal 2. So that's why both of them have a straight line at 2. But how do we decide which is which? They both look very, very similar. Well, we could start comparing some points. So, let's look at some of the points they have. D down here has a point at 0, 1, and C has a point at 0, 1 as well. Okay, maybe that's not the most useful point. But what other points do we see? D has a point at 1, 4, whereas C doesn't really have a whole number point that we can get at. Well, now this is interesting, because one of these exponential functions is going to pass through whole numbers, and the other one is not. Remember that e to the x power is always going to give us these funky answers. But 4 to the x power, we should just take 4 to some power to see what it equals. So if I did 4 to the first power, that'll give us 4. That means that when x equals 1, y should be 4. 1 comma 4, which is exactly the point we got from D. So we can pretty much deduce that this one is going to be D, and this one is going to match C. But again, we now need to solve these equations using this information. This is going to be a little bit tough, because if we have, for instance, e to the x power equals 2, how on earth do we solve for x? Before it was easy because we could sort of glance at it and see, oh, it crosses at 0, 1. But in C, we don't really know where it crosses. It crosses right here at a weird location. Well, remember our solving tricks. According to our solving tricks, if we wanted to solve for x here, let's try converting it into a different form. We could change this into a natural logarithm, because a natural logarithm will have a base of e. We put the 2 next to it, and it would equal x. So all we would really need to do is find what the natural log of 2 is. The natural log of 2, if we plug it into our calculators, is going to be this. Does that seem to match our graph? Does our graph seem to cross an x value of around 0.7? I'd say it's pretty 0.7-ish, right? It's about 3/4 of the way there-ish, maybe 2/3. I think we have found our winner. I think that we have just found that the point is 0.693, comma, what's the y value? Well, since it equals 2, we know the y value has to be 2. I think we found our point. We could pretty much call that a check. And if we wanted to check again, we could just plug it back in to our equation. Of course, keep in mind that it's not going to be an exact number because we rounded here. But e to the 0.693 is super close to 2, so we got it. We can do a similar thing with checking 4 to the x. So remember, 4 to the x equals 2. So let's set up our equation. 4 to the x equals 2. And once again, to solve for x, we should just find a logarithm. This time, since the base is 4, we write it as log base 4 of 2 equals x. It basically asks, 4 to what power equals 2? Hang on a second. Before we go and plug this into our calculators and solve, I wonder if we could solve this one on our own. Because think about it. 2 squared is 4. So 4 to what power would bring us back to 2? Well, the square root of 4 equals 2, but how would we write a square root as an exponent? Recall that 4 to the 1/2 power is the same as the square root of 4. X is 1/2. And just so we can check, let's put in that logarithm in our calculators. We go down to log base. Log base 4 of 2 equals 0.5, 1/2. So we could solve this one by hand, by being a little bit clever with it. The point is 1/2, comma, 2. And if we look in our graph, does that seem to match up? Absolutely it does. It's like right in between 0 and 1. So I'm going to give that one another check mark. From here, we see that these 3 graphs are slanted in this direction. These 3 graphs are logarithmic in nature. Well, we have 3 graphs that are logarithmic here. But hang on a second, there's some differences between these 3 graphs. We have log base 5 of x equals 1/2. We have the natural log of x equals -1. And we have log base 4 of x equals 1. Those 3 are going to give us different lines. And lo and behold, we see that our straight lines here all have different elevations. This is at a height of 1/2. This line is at a height of 1, and this height, oops, sorry, that's the x-axis I was shading in. This one is at a height of -1. So we've already been able to distinguish these. The one with a straight line at 1/2 is going to be E. The one with a straight line at -1 is going to be B. And the one over here, the straight line at 1, is going to be D. So we've successfully figured out what all of these are. Now we just have to solve them. Well, I think the easiest one to solve here is going to be D. Why? Because on this graph here, we see that it crosses at a very specific point here. It crosses at an exact number. That number seems to be 4, 1. Just to double check it mathematically, let's try actually solving log base 4 of x equals 1 by, once again, exponentiating it, turning it from a logarithm into an exponent. That's the same as 4 to the 1 power equals x, and, well, we all know that 4 to the 1 power is just 4. So we would end up getting 4, 1, because the line is at 1, remember? That one was an easy one. It's going to get a little bit tricky from here. Let's take a look and see if we can actually solve E. Log base 5 of x equals 1/2. Well, if log base 5 of x equals 1/2, if we wanted to solve this one for x, we know that we could rewrite it as 5 to the 1/2 power equals x. But once again, 1/2 power is the same as the square root. So what this is saying is x should equal the square root of 5. What is the square root of 5? Well, we know it's going to be bigger than 2, because the square root of 4 is 2, and it's going to be less than 3. Is the x value on here bigger than 2 and less than 3? I think it's just barely. I think it's just barely bigger than 2. Just in case, we can check out our graphing calculator. 2.236, does that look like an x value of 2.236? I certainly think it does. I'm going to call it there. I'm going to say that is our correct x value, 2.236. And the y value is, again, 1/2, because that's where our horizontal line is. Check. Last but most certainly not least, we have to figure out where f intersects. And this one's interesting. It's down here. The equation was the natural log of x, you can see I'm running out of room here, equals -1. Again, to deal with natural logs, we can just flip them. We can exponentiate them. So, if we turn this into an exponential, remember that the base is e. This is e to the negative first equals x. What did we do with negative exponents again? We flip them upside down. This is the same as 1 over e equals x. Now, 1 over e is going to be a little bit tough to calculate, but remember that e is 2.71-ish. If we plug this into our calculators, 1 over e, the e button is right above the division symbol, we get 0.367. So it's about a third. Does our x value look like it's about a third? I think it absolutely does. So we would say for our last one that this is about 0.368, comma, -1. And I'm going to give that the seal of approval. So we have just gone through and solved these equations using a graph. We found where on a graph our two sides of the equation will intersect. Like I said, this is more of a conceptual way of solving it. What we're going to be learning today is a much more feet on the ground way of solving these. So let's flip the page to page number 12. Solving exponential equations. So exponential equations are just another name for equations that have variable expressions as exponents. Basically means that we have variables in the exponents. These look pretty tough, but before we go and solve them, I want to give you a trick. There is a property we can use to assist us greatly here. It's called the property of equality for exponential equations. The math behind it is, if you have two terms with the same exact base, so the same b value here, then their exponents have to equal each other. So if I gave you a problem like 3 to the x power equals 3 to the 5th power, well, we know that this x has to be 5 because they have to match. We can basically treat it as if, when both bases are the same, we can ignore them and just do math in the exponents. So I'll give you another example. Let's say I had 5 to the 12th power equals 5 to the 2x power, and I wanted to solve it. Well, we know that 12 and 2x have to equal each other. So we can ignore the 5's and just do 12 equals 2x, which is x equals 6, when we divide by 2 on both sides. What if we have a problem like A? A is a little bit different because we don't have matching bases. We have 100 to the x power equals 1/10 to the x minus 3 power. Shoot, this kind of seems a little tough. Recall that we are allowed to change a number so that it has the same base. If we can rewrite 100 as some number to some power and 1/10 as that same number to some different power, we'll be solid. We might have already picked up on what number these two have in common. 100 can be written as 10 squared, right? So this is 10 squared to the x. Can we write 1/10 with a base of 10? We absolutely can. That's just 10 to the negative first power to the x minus 3 power. Also recall our rule about power of a power properties. Anytime you have an exponent raised to another exponent, you can multiply them. So this is the same as 10 to the 2x equals 10 to the negative parentheses x minus 3. And now we have the same base. So once we have the same base, it's open season. We set the exponents equal to each other and solve for x. So to solve for x, we need to get x's on the same side. That means we should distribute our negative into the parentheses, giving us 2x equals negative x plus 3. We should add x to both sides, giving us 3x equals 3. And we all know from here that if we divide both sides by 3, we get x equals 1. So our answer here, our solution is x equals 1. Done. If you wanted to check this, you could plug in the 1 on both x's. So 100 to the first power equals 1/10 to the 1 minus 3 is negative 2. Well, 100 to the first power is just 100. What's 1/10 to the negative 2 power? We know the negative means we'd flip it so it looks like 10. And 10 squared is also 100. So of course this is going to work. If we even do it in the calculator, just in case you don't believe me, bam, both sides will equal 100. So we're good to go. What on earth do we do with 2 to the x equals 7, though? That one seems a little bit trickier. Well, we really need both of these to have the same base, but we have an issue. 2 and 7 do not have a power in common. We can't actually turn 7 into 2 to anything. So are we stuck? Do we just give up? Do we start putting our hands above our heads and saying, oh, can't do it? No, we should try a different method. If one method doesn't work, like making them the same base, maybe we try to see if we can get x by itself. Yeah, because there's only one x here. In the last problem, we had to get the same base because there were two x's. We couldn't just solve. But here, we can get x by itself and then plug it into our calculator, right? Some of you keen-eyed viewers might already figure out we can rewrite this as a logarithm. We can logarithmize it. So, if we write this as a logarithm, the base is 2, because that's the number on bottom, the argument is 7, and the exponent is x. Log base 2 of 7 will equal x, or log base 2 of 7 is our answer. No wonder this is difficult to find. This is going to be a crazy decimal. We'll have to use our calculators for this one. If I plug in log base 2 of 7, I get 2.807. So that is what we're going to say x is. X equals 2.807. Technically, we want to use a wavy equal sign because it's approximately 2.807, but it's close enough. All right. That's solving exponential equations. There's two ways of doing it. Make the bases the same, or turn it into a logarithm and solve. Both methods, totally viable. But what about solving logarithmic equations? Well, a logarithmic equation, as you might be able to guess, we mathematicians are not very creative with our names, has a logarithm with a variable inside of it as the argument. In order to solve a logarithmic equation, we should utilize the following property. The following property is, if you have two logarithms with the same argument, with the same base, their arguments will be the exact same. Let me give you an example. Let's say we had, as the example down here dictates, log base 2 of x equals log base 2 of 7. Well, remember what we can do to both sides to solve this. If you want to get rid of this logarithm on both sides, can't we just exponentiate both sides? Meaning, turn it into 2 to the log base 2 of x power equals 2 to the log base 2 of 7 power? We can do this because one of our rules in the previous section was, well, not previous section, a couple sections ago, was that an exponent and a logarithm with the same base can cancel out. We'd be left with x equals 7. So the rule is, if you have the same base, you can just slash out those logarithms. The arguments will equal each other. Can we use this to solve problems? It's a rhetorical question. We absolutely can, and we absolutely will because we're awesome. Let's take a look at A. We have the natural log of 4x minus 7 equals the natural log of x plus 5. It's a natural log with the same base as another natural log, because these bases are both e. We can just slash out the natural logs and be left with 4x minus 7 equals x plus 5. And this one we can definitely just use our Algebra 1 skills to solve. We subtract x from both sides, getting 3x minus 7 equals 5. We add 7 to both sides, getting 3x equals 12. And we divide by 3 on both sides, giving our final answer, x equals 4. Very nice. Can we do the same thing for b? Can we cross off a logarithm here? Well, not quite, because we only have a logarithm on one side. With a logarithm on one side, we can't use this same trick. However, we absolutely can exponentiate it, meaning take it to an exponent. Recall that during our proof of this, we exponentiated like crazy. So to get rid of a log base 2, because that's a little harder to solve for, all we need to do is turn this into 2 to the log base 2 of 5x minus 17 equals 2 to the third power. We have those as the powers of a base of 2. From here, we notice that 2 to the power of log base 2 cancels out. And wait, what is 2 to the third power? That's a number, right? That's just going to equal 8. Y'all, what we have just found is 5x minus 17 just equals 8. And this is absolutely something we could solve for x with. We just have to add 17 to both sides, getting 5x equals 25. Then we just divide both sides by 5. X equals 5. Done. Very nice. Before we go on, I want to share that there is a very unfortunate typo in these sections below. We don't need to do logs. We're only doing one log here. So cross off one of the logs in each of these. This is the problem that we're solving. Log base 10 of 2x plus log base 10 of x minus 5 equals 2. Oh, now this is interesting. We have two logarithms being added together. So we can't just take everything to the 10 and take it to the power of these. We need to be clever. Recall the logarithm rules we learned last time. If you have two logarithms of the same base, and they're being added together, we can write it as if their arguments were being multiplied. This is the same as log of 2x times x minus 5 equals 2. Can we simplify 2x times x minus 5? I think we can. Let's make it into one term. This would be the same as log of 2x times x is 2x squared. 2x times negative 5 is negative 10x. That'll equal 2. And once again, how do we get rid of a logarithm like this? All we have to do is exponentiate it. The base is 10, so we put these as the exponent of a base of 10. That'll cancel out the base of 10 here and the logarithm of 10 here. So what we end up with is 2x squared minus 10x equals 10 squared is just 100. Now we start to see a way of solving this. We have an x squared in there, so we know we want to get everything onto one side. So we can minus 100 from both sides, giving us 2x squared minus 10x minus 100 equals 0. And now we can just use any solving method we want, really. We can factor this, we can graph this, we can do the quadratic formula, we can complete the square, although I wouldn't recommend it because there's an a value. We can use any of the methods that we know. I'm going to choose to factor it since I'm a factoring kind of guy, but you can use whatever of those methods you like. We start by recognizing that all these terms can be divided by 2. It's the same as 2 times x squared minus 5x minus 50 equals 0. And now we just ask ourselves, we need to set up a combinator where two numbers multiply to make negative 50 and add to make negative 5. Pause the video and see if you can figure it out. Hopefully you've had a chance to try this one out. The two numbers that multiply to make negative 50 and add to make negative 5 are negative 10 and positive 5. So we can rewrite this as 2 times x minus 10 times x plus 5 equals 0. And if we look at our x values here, we can see what x has to be to make 0. 10 minus 10 equals 0, so we know x is 10, and negative 5 plus 5 equals 0. So these are two solutions. Recall, however, that we're not quite done. Anytime we end up with multiple solutions, it is very possible that some of those solutions are extraneous. So, the only way to check if a solution is extraneous or not is to plug both solutions back into the original problem. So, let's actually do that. Let's plug in 10 for both x's and see what we get. Log of 2 times 10, well, 2 times 10 is 20, plus log of x minus 5, well, 10 minus 5 is 5. That's supposed to equal 2? Fantastic. X equals 10 works. That is one of our solutions. Let's do the same thing with negative 5. So we type in log of 2 times negative 5 is negative 10, plus the logarithm of negative 5 minus 5 is also negative 10. So it's like the logarithm of negative 10 twice. What's the problem? Oh, that's the problem. We get an error that pops up. Why do we get an error? Why is it not possible to calculate out log of negative 10? Remember what this is asking. This is asking 10 to the what power would make negative 10? 10 to any power is never going to equal negative 10. You can't take an exponent of something and get a negative number. It's just not possible. You can't take an exponent of a positive and get a negative. So that's why this is extraneous. X equals negative 5 is an extraneous solution, so we cross it off. X equals 10 is our one and only answer. I think at this point we have enough practice with these to try out D on our own. What I'd like you to do is I'd like you to pause the video, take a couple of minutes, because D is a tough one, kind of like C, and see if you can solve for X. Pause the video, try it out. All right, y'all, let's begin. First thing we notice, these are two logarithms, the same exact base, and they're being added together, so we can use our product property and write it as if they were being multiplied. This is log base 4 of x times x plus 12 equals 3. And I like to simplify this right away. I don't like seeing two things being multiplied in my argument, so we can just rewrite this as x squared plus 12x equals 3. Very nice. All right. From here, we can do the same thing we did last time and exponentiate both sides. To get rid of log base 4, we write it as 4 to the power of log base 4 of this, and 4 to the power of 3. Well, 4 to the power of log base 4 is going to cancel out, meaning we just get x squared plus 12x, and 4 cubed is just a number. That's going to be 64. Now we see the way to the end. We subtract 64 from both sides, and we solve this like we solve any quadratic. By factoring, by quadratic formulating, by completing the square, by graphing. I'm going to still stick with good old factoring because I like it the most. We're looking for two numbers that multiply to make negative 64 and add to make 12, right? This one was actually a little bit of a tricky one, but we do get two numbers that make it happen. Two numbers being 16 and negative 4. So we get x plus 16 times x minus 4 equals 0, and we get our two solutions. Our negative 16, because negative 16 plus 16 is 0, and 4, because 4 minus 4 is 0. But right away as we check this, we will see that we will get some extraneous solutions. Why? Well, because remember that we cannot take a logarithm that has a negative argument. It's just not possible. At least not with positive x values. If we plug in negative 16 into our original here, negative 16 plus 12 is negative 4. And can we take log base 4 of negative 4? Is there any number that we could take 4 to the power of and get negative 4 as an answer? Not going to happen. We know that our extraneous solution is the negative one here because we can't take a logarithm of a negative number. Done. Our answer is x equals 4. Let's flip the page one last time. We've got, two last time. No, one last time. Losing my mind. We've got one last thing to take a look at, and that's solving inequalities that have exponents and logarithms inside of them. Recall that anything that has a variable expression as an exponent is exponential. So an exponential inequality has an exponent that is a variable in it, whereas a logarithmic inequality has a logarithm with a variable as an argument. Keep in mind, with inequalities like less than, greater than, less than or equal to, or greater than or equal to, whatever rule works for greater than is going to be a rule that works for less than, is going to work for less than or equal to, is going to work for greater than or equal to. So all these rules work with all symbols. The two properties are as follows. If you have an inequality where both sides of the inequality have the same base, we can set the exponents equal to each other. It's the exact same rule as before, just with an inequality instead of an equal sign. Similarly, we have a logarithmic rule. If you have two logarithms with the same base on either side of an inequality, you can set their arguments equal to each other. Fantastic. Can we use these properties to help us solve inequalities? That was rhetorical. We absolutely can. But let's start off by looking at A. For part A, we don't have logarithms on both sides or exponentials on both sides. We just have 3 to the x is less than 20. So what can we do? We could rewrite this as a logarithm. Or, in other words, we can write it where we take the logarithm of both sides. Let's see this done real time. While we could write this as a logarithm, sorry about the bell, everyone. While we could write this as a logarithm straight up, we don't know what sign the inequality symbol would be facing. So instead, let's just take both of these as arguments. Let's write it as log base 3 of 3 to the x is less than log base 3 of 20. Aha! Now we can cancel out a log base 3 and a base 3, giving us just x is less than log base 3 of 20. We've basically solved for x. All we need to do is figure out what log base 3 of 20 is. So in my handy-dandy calculator, I'm going to log base 3 of 20. Bam. X is going to be 2 or less than 2.727. So we write out our answer. We get x is less than whatever log base 3 of 20 is, which is 2.73 or 27. Done. To check this, let's think about some numbers that are less than 2.727, see if we can plug them in for x. I can think of a number less than 2.727. It's 2. What's 3 to the second power? 9? That's less than 20. Or we could think about numbers that are bigger than 2.727 and see if they make this false. Number that's bigger than that is 3. Is 3 cubed less than 20? No. So it is seeming like it's going to be numbers less than 2.727. we're good to go. Once again, we've got this log printing error. I apologize. We're not doing logs here. So here we have the log of x is less than or equal to 2. We can do a couple of things to solve this one, but remember that log of x is log base 10 of x. So we can exponentiate both sides. We can take both sides with a base of 10. So 10 log base 10 of x is less than or equal to 10 squared. If we do that, then the logarithm and the 10th power will cancel out, giving us x is less than or equal to 100. Done. Easy enough, right? Let's take a look down here. What if I had e to the x is less than 2? Once again, we have a case where we can take a logarithm of both sides. If it has a base of e, we want to take the natural log of both sides. So the natural log of e to the x should be less than the natural log of 2. Natural logs and e's cancel out, so we are just left with x is less than the natural log of 2. Hey, didn't we calculate the natural log of 2 earlier? I think we did during that very first exercise of the graphs. We calculated it was about 0.7. X is less than 0.693 specifically. Last but not least, we have this one. And this one is a monster of a problem, even though it doesn't look like it. We want to solve for x here. But before we get rid of the log, is there something we can get rid of first? We should always still check to see if we can use reverse PEMDAS. We start by subtracting 9 from both sides. This will give us log of x is less than 36. What can we do here to get x by itself? We exponentiate both sides. By taking 10 to the power of these things, we cancel out the logarithm, getting x is less than 10 to the 36. I am not about to write out what 10 to the 36 is. That is a 1 with 36 zeros. I'm not doing that. It is a big answer, but x is less than 10 to the 36th power. With that said, everybody, that concludes our notes for the entire unit, actually. That is Unit 6. So I hope you have a fantastic rest of your day. As always, catch you next time.